But before that, they only used to have one vorticity in the direction opposite to the movement, and the one vorticity in the two bottom corners. But now, everybody has not only multiple, but you can have as many as you want depending on your grid. So the grid used to be so coarse, and the dissipation of the numerical scheme used to be so large that it used to eliminate all that. Yeah, 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 right, yeah, yeah. So the point in the context of this multi-phase flow, and as I said, this was going to be the lecture 4 in the notes that you have got, but I decided to make it 3, and because I want to, it is now simpler to go over in the context of the multi-phase and finish it, and then we will go to the third one, which is much more, I would say, engineering applications that people use in the industry, and it doesn't really emphasize ANSYS that much at all. So this emphasizes ANSYS, and this is again, you will find that except the lecture 3, all other lectures are based on the work of my students. Okay, and I haven't done work myself for a long time. Okay, so this is again based on the work of a student several years ago, and the even if you have 8% nanofluid, uh, let me ask you this: that what, based on what we discussed, can you use it as a single phase? Have you tried to? Okay, have you tried to compare that? So then you can use still a Eulerian method, which is there in the ANSYS. Do not use the discrete element at all, because you will be spending too much time and resources without any gain. Okay. So here we are going to assume that nanofluids are not more than 4% in what I am going to show you. Now it is also a free convection example, okay, which is a little more interesting and more complicated, just like the free convection that you have in the cavity. So your free convection is occurring because your bottom plate and the top plate are different temperatures, and probably you have a side walls which are adiabatic, right? Okay. So we are going to do a similar problem, and it is completely based on ANSYS. So I'm going to emphasize that this you can treat as a single phase. Okay. But stop me, if you have any questions, and this is just a general methodology that we use in CFD, that is have a geometry, whether it's a cavity or a pipe or any complicated case. And so the more complicated application of nanofluid will be, what is the application that people will use? Anybody knows that? Okay. You can use it in heat exchanger. You can actually use it in a refrigerator. I mean, there are thousands of applications. The main idea is that you increase the thermal conductivity of the liquid that flows in these devices. So, in case of, you can use to heat it up, or you can use also to cool it up by using the increasing the thermal conductivity. And it turns out that by 2 to 4% addition of a nanoparticle, and you want to keep it small, and small means that you want to keep it at a, it is a micro scale, and so that they almost float like a Brownian motion. You don't want to sediment them. Now people, in the car industry, they have looked at it, they don't want to use it because there are other problems which have not been worked out. So whenever you have these particles, although they are benign, they can hit the wall of the heat exchanger or radiator, and then they get stuck. So in many cases they have found that how to clean them. So right now the fluid, what is the fluid that is most common? Is water. All right, and what is the second phase? Is these particles. So what are the particles that normally you use? So Al2O3 and CO. Yeah, so you can use basically that, and the latest kind of particles people are using is the carbon nanotube, CNTs, and they have some degree of variation in terms of their property. Now, aluminum oxide is one good thing about it is very cheap. Copper oxide is more expensive. Okay, silicon oxide is also cheap, but the problem with silicon oxide is that it sticks to the wall worse than any other one. Okay, and carbon nanotubes are also very cheap. You can order it on Google. There are a lot of companies, and you don't have to worry about it that they are monodispersed or polydispersed or what is the size and etc. Because that is not critical. So it is a single phase flow that I'm going to talk about. And as you said that for 8% you are not getting good results, it could be a factor of many other things other than the model itself. I just gave you an answer, but I think it could be a lot of other CFD related issues that you have. Okay. So the cavity flow, one of the critical issue is that there are singularities at the corner. Okay. So I have already talked about this, and there is no need to belabor on this again. Oops. Okay. So basically, as I said, and all of you know who are doing this, that even 1% by volume, or maybe by 2 to 4% by volume, you can show that the thermal conductivity increases, by as much as 50%, which may be higher number, but normally 20% is a very good number actually. Now this is the only thing that I will show in the entire course where the experiment was also done by my best student. Normally I don't do the experiment. Okay, just like last year in the course, I showed an example where only one experiment was done by my student. Okay. So in this case, it was very cheap experiment actually. It didn't cost anything, and so we just want to test it for a free convection. As I already mentioned, radiators, engines, the air conditioning systems, and microelectronics that you mentioned, they are being quite powerful devices. It turns out that nobody in the microelectronics industry wants to use nanofluid anymore. And a part of the reason is that, again, you have to have the right, because those channels are so little that the effect of these particles, can become really overbearing. And so you want to make sure that the cooling effect that you are doing, other properties are met. So cost is not that much of an issue, but of course the whole chip is silicon, right? So you want to make sure that everything works properly. Okay, but these are the applications, and again, the problem I have told you that you use Fluent to do this problem. So the problem is here, and what you have is that you have basically a cylinder, and oops, I think this must be okay. So in case your cavity, you have the bottom wall and upper wall. And in this case, we have the higher temperature and lower temperature, cooler wall, and the rest of them are adiabatic. This is a standard model. And then, of course, you can have it vertical. Then you have a free convection going from hot to the colder fluid by buoyancy effect. And so this is basically the model. And then, yeah, he has done a lot of work on this area. He has done some good work on this area. Yeah. Actually, this whole field was started by a person at Argonne National Lab. And now there are books written also on this particular So the topic, the whole field has come a long way. Okay, and the applications are also now coming along, particularly in the auto industry, and also some people are trying to do with the refrigeration. But I have not seen anybody using so far, but maybe they will for MEMS. But it is a very powerful, way to do it, and very cheap way to do it. So this is just now many of you who are interested in basic CFD, you know that you can generate a structured mesh, and of course, I again always emphasize that make sure that whatever mesh you have, the solution that you at the end you get, considering everything being equal, should be independent of the mesh. Same algorithm, same boundary condition, everything same. Then you want to make sure that the mesh independence is there. Now that you can see whether it is 1% different or 2% different for some quantity. So in this case, it could be Nusselt number as a function of Rayleigh number. Okay. So this is just to show you a picture, and then this is of course the vertical cylinder. That was a three-dimensional view. The other view, and so the conservation equations which are built into the fluent are the standard equations. Now in this particular case, it's important, I want to ask this question, whether it is incompressible or it is a compressible solve. What would you like to use? No. The equation, doesn't matter what you write, the general form of the equation. What exactly is needed? So you need an incompressible flow solver because the velocity is very small, as we discussed, before. So for you, that is incompressible is okay. So if you do the incompressible, you can just take the rho out. Okay? Doesn't matter. But of course, there are time, you are looking at a steady flow, so there is no time dependence, which means that you have to have a pressure velocity coupling. And the pressure velocity coupling is provided in the fluent. How? Anybody can tell me? Because I know everybody in this room uses fluent. So how is the pressure velocity coupling? Because you see this equation only has velocity, and there is a pressure here in this tau, which has viscosity plus the pressure term. And so simple algorithm. So the main simple algorithm is the Patankar-Spalding algorithm, and that was a major breakthrough actually to provide a pressure velocity coupling. And pressure velocity coupling is nothing but calculating the momentum equation, and from there you get the pressure and you correction and put the pressure correction into the continuity equation to get a Poisson equation, and then solve the Poisson equation by relaxation. So that is the basic gist of the Patankar-Spalding algorithm. So that is what you do, and now the effect of the free convection comes in here, and that is a Boussinesq approximation to approximate what? The buoyancy force. So the buoyancy force is given by proportional to the temperature difference, and that is the Boussinesq approximation. And so that is given here, and then of course rest of the equations are the same. So you have to know before you use why are you using in the fluent to get the right answer and in the shortest possible time. But don't forget about the mesh independence. And then, as I said, you have a Boussinesq approximation, rho is constant, use a simple algorithm, and then there are variations of simple C, piezo, and this and that. But to keep life simple, just use simple, and that is good enough. And you can use a pressure-based solver because it is compressible flow. So this is the Boussinesq approximation. Now here the beta is the coefficient of thermal expansion. Now this is important because we are trying to deal with the heat transfer problem. Okay. So now, of course, I'm not going to go into the details. It's a finite volume method, and so you do the finite volume method. Why do you use? Let me ask you, those of you, all of you are expert in CFD, that why not use the finite difference? What is the difference between finite volume and finite difference? Okay. Anybody else? So that is the right answer. Because what happens is that in each mesh cell, the mass and momentum, along with the forces acting on these interfaces, they are conserved. So if you take the whole volume, the entire computational domain, you can totally assure that the mass and the momentum and energy are conserved within a truncation error. But if you take the finite difference and do the finite difference discretization and the first and second order derivative, the error is substantially more. So your answer is absolutely perfect, that you are conserving on each little piece the volume. It's similar to finite element. So as you can see that it was useful to discuss with you that, so that I can integrate some CFD ideas into simpler models rather than talking about multiphase. But tomorrow we will discuss entirely the modeling of multiphase in the context of fluid. So anyway, this is not that important. All of you know the finite volume method. Now this is comes the two-phase problem, and we are going to consider it is a single phase. The particle size is very small, so micro size. There is no sedimentation. There is no, almost the effect of gravity is nil. The only effect of gravity is the buoyancy force. Okay, but that buoyancy force affects it as if it is the entire fluid, just like in this room. It doesn't affect it to the individual particle. Individual particle has no effect of the gravity at all. So that is the approximation that we are doing. Okay, and so what we are saying is that the multiphase fluid consists of the liquid and the dispersed particle. That's it. And of course, whether they are monodispersed or they are polydispersed, etc., doesn't matter. As I said, in the aggregate of things, it doesn't matter. And then, of course, it is a single phase fluid, as I told you. And my limit here is about 5%. So maybe you are little beyond that, 8%. You can look at the oil area and 2 fluid model if you want. So now, what is the difference by having a nanoparticle? So the difference is that all the properties now change. So the viscosity changes, the density changes, the thermal conductivity changes. So all the properties of this fluid, which has this small percentage of nanoparticle, whether it's aluminum oxide or copper oxide or carbon nanotube or silicon oxide, they all change. This is the tricky part, because if you cannot model these properties correctly, then none of the other numerics is going to help you. Because if your viscosity is wrong, then you are going to get a wrong answer. Okay. So it may not be the percentage, of the nanoparticle alone that may be causing the problem. That how are you modeling the property of silicon oxide versus aluminum oxide versus, other material is very critical. Okay. So the people like, for example, S.K. Das that you are mentioning, who has done a lot of work in India in nanofluid, he has spent a lot of time in figuring this out. All right. And of course, there are a lot of other people uh, in United States who have been doing that. A lot of people are doing this. Okay. So now you can see here that this is a particle thermal conductivity. So it depends on what particle you have, and this is the fluid. So whether you have water or you have some other stuff, that becomes fluid. So this is a formula which is called the Maxwell model. Okay. Now the P is the volume fraction. So we are considering not more than 4-5%. So this can be considered a single phase fluid. That is where people are making a lot of contribution. Is this a good model? So people have now done, work like a kinetic theory based models, going back to the simulation ideas from Boltzmann equation, and all kind of physicists have got involved. So the basic thing is that, is this a good model or you need something? But for if you just want to try out how does it work in Fluent, then you can choose this is a reasonably good model. Okay. Or otherwise, there are more latest models, but they are all algebraic. They are not very fancy. But that algebraic models you can substitute and keep trying. Okay, so this is the kinetic model, and this kinetic model, that S.K. Das was involved a little bit, but this is again a version of it. People have done a lot more, and so this is a kinetic model is more sophisticated. So there is a fluid phase thermal conductivity, and now it has a more complication in it, and that is the surface area of the fluid particle, which the previous one did not have. So it means how little these particles are, how big they are, they do influence the whole thing. The rest of it is the same. So what is different is that it is the radius of the fluid particle versus radius of the nanoparticle, and so it has a little more complication, but in terms of implementation it doesn't really matter. You need a little more information. Now density is very straightforward. Any place you go, this is the end density. All right. So it is P, so particle versus the density of the fluid. This is a very simple formula that you will find in every textbook. Now this is a specific heat. This is also a very simple formula. You will find in every textbook. This is the viscosity, and there are only two type of relations people use, and now they try to do a little better, but in viscosity case there are actually some little trick. And one is that, of course, this is Einstein's relation, and this is assuming that the fluid particles are moving in Brownian motion. That is how Einstein derived in 1902. And then, of course, this is a additional complication that people add, and that is the effect of temperature on the viscosity. And this is not a universal relation. You can fix your own thing, like people are using some analog of the Sutherland's law, some power law, etc. But you can use, this is the one that this particular paper has used. So this is again has effect, the particular effect of temperature, but this formula is very much used based on the fraction of the fluid element. But the major physical assumption is that it must be in Brownian motion. And then, of course, this is a what is called a Brinkman formula, which people prefer it, and again you have a little more complication in it. Okay. So these are all the properties, and then beta is the thermal coefficient of expansion, which we know is a function of temperature. And of course, there are correlations that they can fix in the temperature range that you are interested in. So this is about 20 degrees centigrade to maybe, I don't know, 50 degrees centigrade. All right. So if you look at all these properties that you are needed, you can just put in Fluent in 1 second, right? I mean, you don't even need to write a UDF actually. You can directly substitute these numbers into. But if you want to add these formulas, you can write a simple UDF and plug them in. All right. So, a very, very simple multi-phase flow of particles plus the fluid, but you are treating it as a completely single phase flow without any other addition at all. And then you are solving a new problem by treating it as single phase, but you have to be aware of what the assumptions are. Okay. And again, you have to go through all the mechanics, which means that you model everything correctly, the grid is correct, and boundary conditions are correct, etc. So that you have a confidence that you are doing the right thing. So whatever we have done, where is the trick? in getting the right answer. In the material properties, where is the trick? It is in K. It is in the K. The expression for K, where we had a kinetic model and Maxwell model. The people have now made a lot of other models. I don't even know their names actually. But there are a lot of models because people are spending time to improve these models for a class of material. Like for CNT, for example, carbon nanotubes, I saw some other latest model that people have worked on, and they seem to be very effective. And carbon nanotubes are very cheap. All these things are very cheap, with the exception of copper oxide. Okay, so if you want to make a technical contribution, you have to figure out how to model the thermal conductivity of a particular type of particles that you are using of a particular size, and it should capture the effect of the nanofluid correctly. So if that model is wrong and everything else is correct, you will never get the right answer with respect to the experiment. Of course, possible also the experiment is bad as well. Okay, so where people say that if somebody has performed an experiment, everybody believes it. And if if a person has performed a CFD simulation, only the person who has performed it believes it. Nobody else does. So you are in a tough territory actually. So that is why the careful implementation and validation is very important. I have spent all my life in CFD, and if you brought something, I will not trust it myself. Okay, except I know if I am doing it, I will probably trust it. The reason is that you have to go through this machinery, or what we call building blocks of CFD, and know how to implement it correctly. And in this particular very simple application of multiphase flow, but it is actually what we call is a fake multiphase flow, if you want to call it, because you are using a simple fluent and just adding some algebraic relation, but that is a key part of the whole game. But now you can go through this procedure that you all know. And then how do you represent the results? And if you remember in the previous presentation, I said that in fluid mechanics, in general, whether single phase, multi-phase, you want to see what are the most important dimensionless parameter to represent this solution. Is Reynolds number, Mach number, and we just or like Bond number, or Morton number, or Weber number, or Capillary number, and so on. Because then you can reduce the data from 65 people onto a curve, which becomes a universal answer. So that is important. So in this case, the free convection problem that we have, we are using the Nusselt number, which is defined as this heat transfer coefficient parameter H, and then there is a flow rate, diameter, hot and cold wall, thermal conductivity, and the Rayleigh number. So all the plots that I will show you and people in free convection do is that they plot the Nusselt number, which is a function of the wall property, but the K is a very important parameter. K is a very important parameter because this is what the nanofluid is all about. And the Rayleigh number is of course like a Grashof number, and then again you have this coefficient of heat transmission or whatever is the Boussinesq coefficient, temperature difference, kinematic viscosity, and diffusivity. And so we will plot this Nusselt number versus Rayleigh number for different temperature differences and different length to the diameter ratio of the pipe. So this is what you get, and I am telling you that the experiment was done by us, and the calculations were done by mesh independence, second order accurate scheme, and so on. So what you see here is Nusselt number, and the Rayleigh number of course is always very large. So the values that you see is of the order of like 2 million going to 20 million. and the Nusselt number is also going about 12 or 14. So these are the general numbers which are there. And so now you can see that as the Rayleigh number increases, the Nusselt number increases, which means there is a more heat transfer. So it is doing the job, what we have, but the discrepancy is there. So you have the red versus the blue, and you can see that red is giving you a higher answer than the other one. I am showing you this result with pure water, so there is no nanofluid at all right, and a small aspect ratio. So this is just to show you that even for a pure water, where the Maxwell model or kinetic model, nothing matters, there are some issues that they are not matching. Okay, so but whether it is a okay result, it depends on the person who is looking at it. Right. So it may not be acceptable, but I think that the experiment that was done also was very crude actually. But I am not justifying either of them. So now you see here, and now we have 1% of aluminum oxide, and then you can see there is more closer relation, but it's still at the three different places where the data was taken for the Rayleigh number. Again, there is some discrepancy there, even 1%. And now you go to 1%, then you have, I think this is experiment, and this is aluminum oxide with a kinetic model, and this is with a Maxwell model. So this is the Maxwell model, and this is the kinetic model, and this is the experiment. So the kinetic model is slightly better, but it is not perfect. And both of them prediction are higher than the experiment, which is in blue. So now there is a potential here to make more improvement to that. But you cannot actually just come up with some fudge factor. You have to have some logic behind making a change. Because if you can just come up with some fudge factor to fit the data, then it will turn out that for some other problem it will not work. So you have to have some logic even when you are doing the empirical relation. So now this other one with a 4%, and so the trend is in all the cases similar, that the experiment versus the calculation, the difference is there, okay, by few percent, and also the difference is higher in the same trend between lower or higher value, except one case that I showed you. Now here you have 4% in water, and again you have the kinetic model, red one, then you have this Maxwell model, and this is the experiment. So you need to fix this problem, but in all cases kinetic model is doing well, and this kinetic model is by one of the persons, S.K. Das actually, who is in India. I don't know where he is right now. Okay, O.I.D. Roper. I see. Yeah. Okay. So now you see that this is Nusselt number of pure water again, but it is now L over D is 1. So the aspect ratio is larger, which means there is a lot more room for the heat to transfer in the buoyant fashion. And then again, this is 1%. You can see that the difference between the calculation and the experiment, calculation is always in red, and then again you can see Maxwell model and the kinetic model and the experiment, and the trend is similar, that kinetic model is better. So these calculations go on to show that there is a kinetic model which is better, everything else being equal. So there is a room for improvement for K. Everything else is not going to matter that much. Yeah. So if you have a small size particle, and this kinetic model actually uses the size of the particle also, which Maxwell model doesn't. The Maxwell model only uses the Kp, the silicon oxide, or that is the carbon nanotube, etc. But that kinetic model has one advantage, that you are using the size of the particle. But the Kb is valid only for a certain size of particle. Otherwise, the Brownian motion is violated. And now, all this in use of that, I am not sure, because I don't know that there may be some kind of empiricism of some kind is involved, and so that may affect the result. Because all these models, you are trusting the people who have developed it, and they have used some theoretical basis for it, but it doesn't mean that this is the end. I mean, you might have to improve on it. But one thing is coming out, that kinetic model is doing better. Okay. Now, then maybe if you add more correction to it, whether the fluid is in Brownian motion or not, that may add to this also information. And also, I don't know the effect of the other parameter like beta and also the mu, but I think that is, whatever I know, is a small effect. That is correct. No, no, but what you are telling me is that if you put gravity to be zero, uh-huh. Now, what he's saying is that the default value of gravity is 9.8, right? And so, even if you put in 0 or 2 or 5, it must go back to default value. No, no, but listen to me. I'm not going to argue here. I don't know exactly what is going on, but I would certainly say that to conclude, for whatever calculation you did, that gravity has no effect, I think you should not look that way. You see, you got some result, and suppose you did some experiment, numerical experiment, and it's varied the gravity from say 1 to 10, and you got no effect. So you have two choices to interpret. One choice is that you can declare that the gravity has no effect. The second choice is to look into the fact that what is wrong where, whether it is using a default value or there is something else is wrong in your calculation method, that gravity is showing no effect. Because if the gravity is not, has no effect, don't trust the solver that much, or don't trust. No, no, I don't care what it is. It could be fluent or it will be some God given thing. You cannot believe something which is physically violating. Okay, like there are a lot of people papers on the Google. They say if you do that, people still believe the earth is flat, right? Okay. Now, my personal observation is that earth is flat. I have never seen the round curvature of the earth ever in my life. All right. Have you seen that earth is round? I don't think so, because fluent has been applied to a large number of cases. So like tomorrow or day after, I will show you where the gravity is a important part of the multiphase flow. Like yesterday, I showed you 6 different cases and a vertical pipe. The vertical pipe, you had a bubbly flow, you had a packed flow, then you had churn flow, you have annular flow, the slug flow, and whippy flow or whatever, and they are all affected by the gravity, in contrast to the Moody diagram that I mentioned. So, to say that gravity, I mean, it is okay to say that if I neglect the effect of gravity, there is not much effect, all right. But to say that you change the gravity and the solution does not change, then, and it is a free convection problem, it means that you have to look at what is the reason. If it was a forced convection problem in a horizontal pipe, and then if you do not have it, it is okay, all right. Or if you have an aeroplane flying at 50,000 feet or whatever, you neglect the effect of gravity, in calculation of the lift, it does not matter, okay. But when you are calculating the mass of the aeroplane or weight, you must have the gravity in it, because otherwise you are violating the physical principle, okay. So your question is that somehow fluent gave something, it means that you have to look deeper the problem, okay. So these are the kind of solutions that we are getting, and you can go into details, I am not going to go over it. You have the notes in your hand, and so they, all of you, as I said, as you can see that whatever we did, the experiment has variation, and this is, you know is the one that we have. Now when I look at this result, okay, and then I have a little more confidence in the fluent rather than the experiment, okay. So experiment is also not perfect, and also what kind of technique you have used. So if you use more sophisticated heat transfer measurement, then you can get, like you have these uh, thermocouples and others, or you have very crude way, then there could be some difficulty. So when you submit a paper to a journal, and a lot of journals have this policy, like International Journal of Heat and Mass Transfer, or Journal of Fluids Engineering, etc., that you have to quantify the uncertainty both in the experiment and in the data and the calculation. If you do not quantify the uncertainty in your calculation and in the data, it will be rejected. So you have to know the limitation as much as you can, even if you have not done yourself. So you can see, there is other comparisons that I am not going to go over now. There is a aluminum oxide with a 4%. So there is a lot of information there, but there is one consistent theme you will find all these results, that the kinetic model for K is doing better than the Maxwell model. So the message here is that considering everything is done correctly, you have to improve the model K for K, and it turns out that if you now do the literature search, this is 4-5 years old. I don't know. I mean, I showed you in the first slide. I don't remember. No, it is not the effect of thermal expansion. We have total confidence that the effect of mu is very small, because they have been done with both Brinkman model and the Einstein's model with the temperature effect. There is a small effect, and the thermal expansion beta is a small effect, but this is our conclusion that is the effect of K that is the most important, and that is showing up in the kinetic model. And now, as I said, that there are tons of models there. And if you are, I mean, we are not working on this project. So somebody wants to do it, they can try it. Fluent as it is, by simply changing all these values of rho, mu, Cp, K, beta. Okay, and then you can get some results. all right. So it means that a multi-phase flow is behaving like a single phase flow, but you have to know that it's a very dilute flow, dilute percentage of by volume. And also they need to have other criteria that these particles are not affected by gravity and they are kind of floating around. But the fluid is affected by the gravity. It's a free convection. Okay. So don't think that the fluid is not affected by the gravity. So you need to know the physics, you need to know the model, and then you need to know the tool, and then you need to know how to use the tool, and then once you get something out of it, then you have to have a confidence whether it's correct or right or wrong. Okay, all right. So you have to go all these steps to do this. But nowadays, what happens is that we just directly go to the tool, all right, and start plugging it in, right, and get the answer and get these beautiful pictures. Okay, and it works. But sometimes you may work. I mean, I don't know. But that is where actually I find mostly happening. So nobody knows what is inside the tool and how to use the tool. But first step, if it is not correct, then the rest of the things, if you follow, even if it turn out in the end by hook or crook or something to be correct, you have to justify that why it is correct, not for anybody else, for yourself. Okay. So these are all similar results. So basically, you can go over these results. So the main message is that there is a room to improve the model, and I think that would be same case for the cavity. And also, from there you can look at, but your cavity that you have, what is the dimension of that cavity? 1 by 1 is a normalized dimension. No, but you are saying that you are going to use the micro electromechanical system. There is one thing very important, and that is why you may never be getting a good result. For the application that you have, the fluid doesn't stick to the wall. Do you know that? You know that or not? In a micro channel and a micro cavity, one of the physical effect that occurs is that fluid doesn't stick to the wall. There is a slip, and to determine how much is that slip is not an easy thing. That is an empirical relation that you have to use again. So in addition to the Maxwell and kinetic model, etc., if you don't take into account the slip correctly, even with a 0% nanofluid, you have to make sure that you do it right. Then your answer will be all wrong. And in a micro electromechanical system, the size is so small that the fluid slips. Whether it's water or whatever it slips. Air slips. Okay. So if you have micro channel, what are the two physical effects that are important? One is the slip, and the slip is a function of the fluid and the wall, whether it is a rough wall or a smooth wall or what kind of wall effect is. And the second is the length. Okay. Because it is slipping, so what happens is that if you start slipping, then what happens as you move forward? You slip more and more and more. Ultimately, you slip a lot. Okay. So how do you quantify the effect of slipping? But if it is not slipping, eventually what will happen? If it is a laminar flow, it will become parabolic. If it is turbulent flow, then what would happen? Now, flat is okay, but what is the name? The 1/7th power law, right? Yeah. But if it is slipping, even in a laminar flow, it will keep on slipping, and it will keep on increasing this slip. So if you are not taking that physical effect correctly in your modeling, the fluid is not going to help you. Right. It doesn't matter, as I said, you may have a 0% of nano the liquid, because you are using as a single phase, that is a separate issue. The fluid itself is slipping. So, it is a single phase fluid that is slipping, not a multi-phase fluid slipping. But if it is a truly multi-phase fluid with creating bubbles or creating a slug flow, etc., then it becomes even a harder problem. But then you use as a plug, push and then see this slip. Okay. So, as I said to you, first know what you are trying to solve and what is the correct physics, then what are the correct equations, then what is the correct code, and then you use the CFD. All right. But in between, if you don't have to use any of this and get the right answer, is okay. But you have to justify. You have to justify everything. Okay. So this is basically the lecture 4. Anybody has any questions on that? Yes, sir. Yeah. So that is important. So if you paid attention, or otherwise you can look in the notes. There were two lengths considered. One was a small aspect ratio. So L over D is 0.5. But the temperatures are the same. So L means the length is this, and the D is, so is a fat pipe with a very small length. So the temperature that is transferring from the bottom to the top has a very large gradient. But the other case I showed you was 1. So the diameter is 1 and the length is 1. So the temperature gradient is a little more gentler. Because the temperature hot and versus the temperature cold is the same. No. The thing is that fluid must flow. Because if the fluid is not flowing, then we have a static fluid. The fluid is flowing. Say it again. 45 mm? I don't think so. I mean, I don't know which slide you are talking about. But yeah. Mhm. So this is the static temperature at the wall. So in this case, of course, there is no slip. It is a fat cylinder. So it's a boundary condition is such, but this is a temperature. So is a temperature at the wall is a hot wall, and then the temperature on the other wall is a cold wall. This is not a velocity profile. So the variation, what you are saying is the variation in the calculation, which are the black dots, right? So they are almost flat. So it means that the bottom, bottom of the cylinder, okay, is 0, and the top is 1, and so the hot temperature is the top left hand side, and the cold temperature is the bottom